Okay, in section U4A4, so we're on unit 4 and we're activity 4, what we're looking at are standing waves. So a standing wave occurs when we have two waves of the exact same frequency and amplitude and they run into each other from opposite directions. What happens? Now, these are very important in music, these standing waves. Be sure to look at the animations in content 1 to see what a standing wave looks like. This is going to be what the wave diagram of a standing wave looks like. And question number says, what is the wavelength of a standing wave? Well, how do you know when you've got the wavelength of the standing wave? You go past 1 and you end at the second node. So we start here, we go past 1 node and we get to the second node. Okay, we do that. There's 1, 2, 3, 4 wavelengths. So basically, we've got 4 waves in 10 centimeters. 10 centimeters divided by that 4 is going to be 2.5 centimeters. So this is one complete wave right here, or one cycle that we've gone through. Now, if it says that our standing wave has an amplitude of 0.3 meters, what I want you to look at is amplitude is from the midline of the wave to the top. So if that's 0.3 meters, what is the height of the original wave? Well, remember, we have constructive interference here. So the original wave is 0.15 meters. We know that they are both the same because we said to make a standing wave, we need the exact same, I'll just back that up here, we need the exact same frequency and amplitude of wave happening here. So if this is at 0.3 meters and we have constructive interference, that means we need two waves that have run into each other, one from this end and one from this end by definition. So a standing wave is same frequency and amplitude, and they run into each other from either end. So that means our amplitude of each of the original waves would be 0.15 meters. Now, what if we ask the question, what is the velocity of this wave if the given frequency is 20 hertz? Well, we know from earlier that velocity equals frequency times wavelength. We have a wavelength of 2.5 centimeters, so we wrote that down. We have 2.5 centimeters. Now, what you have to understand here is we have to use meters. So that's 0.025 meters. Okay, so we have to divide by 100 to get that. We say our frequency is 20 hertz. So it would be 20 hertz times the 0.025. And that would give us our final answer. Let's see what we have. 20 times 0.025 equals 0.5 meters per second would be our velocity. Now, if you've heard of harmonics before, what they try and do here is they try and explain what harmonics are using these standing waves. If we have a standing wave with a string and that standing wave takes up, so let's say we have a border here and a border here, and this end allows us to try and make a wave, what we have here is half a wavelength. So a fundamental harmonic takes up the whole distance between the 2 points right there. So we call this the first mode. It's the fundamental frequency for any wave. Now, if we have a node in here, then this is half a wavelength. Whoops. If we have a node in here, this is half a wavelength. So if we start from here, there's half the wavelength, there's the complete wavelength right here. This is an octave above the fundamental. So when in music, we have to be very precise, okay? We don't want to have a part of a wave in there. We want to be in full waves or half waves. We call this the second mode or the first octave, and it's equal to 2 of F0. Here we have 3 half waves. This is called the third mode, and it's the second overtone. Then we have the fourth mode, and this is the third overtone. There's a mathematical relationship here that you have to try and understand as you're going through the content. So in here, in this U4A4, what you have to try and understand is what a standing wave is, okay, what a standing wave looks like, how to do some basic manipulations of the standing wave, and also try and understand fundamental frequencies and modes and see how they fit into music.